Hey everyone, in this video we are going to learn about codes. So we'll start with a brief introduction to codes and then we'll talk about some most commonly used codes within the computer systems, namely BCD, binary coded decimal, gray code. Then we'll take a look at how to convert gray to binary and binary to gray. Then we'll talk about 2421 code, XS3 code, ASCII and Unicode, and then we'll conclude this discussion with error detection codes. Alright, so since computers only understand binary information in the form of zeros and ones, we need a way to express our numerals, symbols, and characters using 0 and 1s. We need a way to convert our high-level language into low-level language. This is what codes allow us to do. So let's first start our conversation with BCD, that is binary coded decimal. Now, this is different from your binary code, which will become clear in a moment. See, BCD is a system of writing numerals that assigns a 4 or 8-bit binary code to each digit of the decimal number system. So this is what it looks like. For each digit of the decimal number system, packed BCD allocates 4 bits, whereas unpacked BCD assigns 8 bits. Alright, now as you can see, this is not the same as your regular binary. Alright, for instance, if we had a decimal number 91, in BCD format, first packed, where we use 4 bits to represent each digit, it would be written something like this. So 4 bits for 9 and 4 bits for 1. In unpacked BCD, we would simply have to allocate 8 bits to each of these digits, so 8 bits for 9 and 8 bits for 1. Now, as you're already aware, in binary, 91 would be represented like this. So this is different from this. So this is all BCD is. Very simple. Alright, now let's talk about the advantages and disadvantages of this specific code. Now, on the plus side, BCD helps achieve a more accurate representation and rounding of decimal quantities. It also enables easy conversion into human readable representations. You see, in case of binary, you have to repeatedly divide the given decimal number by 2 and then take a look at all your remainders, right? So BCD relatively is far more simpler than that. So it allows easy conversion into human readable representations. But on the negative side, BCD causes small increase in the complexity of the circuits. Now each digit is going to be represented by 4 or 8 separate bits. So the overall amount of memory you require and the complexity of the circuits involved will become a bit more complex. And then when you use BCD to perform arithmetic operations, you can imagine the overhead involved. Plus, it also results in a slightly less dense storage naturally. Alright, the second kind of code that we're going to talk about in this video is gray code. Now, also known as reflected binary code, the gray code is an ordering of the binary numeral system such that two successive values differ in only 1 bit. Now, this is gray code for all decimal digits from 0 to 15. You can have digits farther than this, but this is just for illustrative purposes. Now, if you look at this closely, you know that each of these representations, representation for 0 and 1, and then 1 and 2, and then 2 and 3, and so on, only differ by 1 digit. Only 1 bit changes when we move from 0 to 1, and then from 1 to 2, and then 2 to 3. Like you can see, here only this bit is changed. Then from 1 to 2, only this bit is changed. And then 2 to 3, this 1 is converted to 0. And then from 3 to 4, this 0 is changed to 1. So every successive digit differs from the previous one in only a single bit, and that is what's special about gray codes. Now, gray codes are most frequently used in analog to digital converters and for error correction in digital communication. Now, the advantages of gray code. Now, on the plus side, with gray code, the switching activity is reduced because you can see that only one digit changes, only 1 bit changes in consecutive code words. So switching between different digits becomes simpler and faster. This results in low power consumption, faster response, and reduced error encoding. These are the advantages of gray codes, very good advantages. But on the negative side, the gray code is not suitable for arithmetic operations. Also, it has limited practical use outside of a few specific applications. For applications such as error correction and analog digital conversion, gray codes are very effective. But outside of these, they offer limited utility. Alright, now that we've talked about gray code and you're already aware of binary code, so it would be a good idea to see how gray code is converted to binary, and then we'll take a look at how binary codes are converted into gray. So first of all, this is a circuit for gray to binary conversion, right? This is the input, this is your gray input, right? The number or the digit in gray code, and this circuit will produce as output binary equivalent of this input gray number. And the equation that you can kind of see from this circuit itself are these. This is how each bit of the gray code is converted into corresponding bit of the binary code. So this kind of circuit performs something like this. So if you have a 4-bit gray code, this will be the resultant 4-bit binary code. So you can see these are the 4 bits of the gray code, these are the corresponding bits of the binary code. And this conversion you can easily see from here, and you can use these equations to perform this. Let's take a look at a quick example to see how to convert a given gray code into binary. So suppose this is the code we're given, 1110, and we're supposed to convert this into binary. Alright, using these system of equations, let's see how to do this. So this is the given gray code. The 4 bits A, B, C, D are 1110. Now we're going to start from this side. Okay, so the first bit remains the same. You can see here B4 is the same as A. Alright, MSB remains the same. So the first bit remains the same. This is our binary. This is the gray. Alright, so the first bit remains the same, and then you're supposed to XOR this with the second bit of the gray code, which gives us the next bit of the binary code. And then we XOR this with the next bit of the gray code, which gives us the next bit of the binary code, and then this is XORed with the final remaining bit of the gray code, which gives us the final remaining bit of the binary. So you see, we've converted gray to binary, and the equations are these. This is it. Alright, now let's do the reverse of this. Now we are given a binary code and we're supposed to convert it into gray. This is a circuit that does that. On the input side is your 4 bits of the binary code, on the output side are the 4 bits of the gray code. These are the system of equations, and using these, this is something we get. So binary to gray. Again, let's take a look at an example. Suppose we need to convert this binary number 1011 into gray. The equations we'll use are these. It's very simple conversion. So this is the given binary ABCD 1011. Now the first bit remains the same. Again, you can take a look back and see from the equations, the first bit remains the same. The next one, we XOR the first and the second bit of the binary code to get the second bit of the gray code. Then we XOR the second and third bit of the binary code to get the third bit of the gray code. Finally, we XOR the third and fourth bit of the binary code to get the final bit of the gray code. So this was the binary, and you've converted it into gray. So all you need to remember for these conversions is either the circuit or directly the equations. Either one will do. The next code is 2421. 2421 is a weighted code. In a weighted code, the bits are multiplied by the weights indicated. Now 2, 4, 2 and 1 are actually the weights, right? So each bit corresponding to its bit position is supposed to be multiplied by these weights, which gives us the number, right? The sum of the weighted bits give the decimal digit. For example, suppose we have a bit combination 1101, and if you're going to represent it using 2421, the decimal equivalent you would get is 1 multiplied by 2 plus 1 multiplied by 4 plus 0 multiplied by 2 plus 1 multiplied by 1, which will give us 7. So this is what a weighted code is. So 2421 is a kind of a weighted code. 2421, each of these digits is essentially a weight. So this is what 2421 code is for decimal numbers 0 to 9. Now here's a slight note here. The BCD code that we talked about in the previous video, binary coded decimal, it's also a weighted code. The weights in that case are 8421. So that's why it's sometimes also called 8421 code. So what you can do is you can go back, take a look at that video, and you can actually verify that. So if we were supposed to convert a given BCD number into decimal, it would be done like this, except the weights would be 8421. So the first, for instance, if we have this, then the first bit position would be multiplied by 8, plus the second one would be multiplied by 4, plus the third one would be multiplied by 2, and the final one would be multiplied by 1. So you can verify that very quickly. Alright, next code, XS3 code. XS3 code, very simple. The trick is in the name itself. You take a BCD code and you add 3 to it, and then you get the XS3 code for that BCD number, right? So this is the binary for 3. So all you do is you add 0011 to each BCD representation, and that gives you the XS3 code, right? So this is the XS3 code for all decimals from 0 to 9. And you can actually verify. You can take the BCD of all of these decimal numbers, add 0011 to it, and you get XS3 code. Simple. ASCII code. Now ASCII code is something I think you might have heard before. ASCII stands for American Standard Code for Information Interchange. This is the standard code commonly used for the transmission of binary information, the most commonly used code. Each character in ASCII is represented by a 7-bit code, and sometimes an 8th bit is inserted for parity. We will talk about parity later. This is your ASCII chart, and this gives you the ASCII equivalents, ASCII codes for all numerals, all letters, capitals and small, and all symbols. Alright, so this is the ASCII code, and you can see that every numeral, alphabet or symbol is represented using 7 bits. Again, an 8th bit is sometimes added for parity. The next code is Unicode. Unicode is an IT standard for the consistent encoding, representation, and handling of text expressed in most of the world's writing systems. So any language, any writing system you can imagine, Unicode provides a consistent encoding, representation, and handling system for that writing system. Now the standard is maintained by the Unicode Consortium, and as of March 2020, there is a repertoire of 143859 characters. Now these characters consist of graphic characters as well as format characters, with Unicode 13.0 covering 154 modern and historic scripts as well as multiple symbol sets and emojis. So anything you can conceive of, any kind of written communication system you can conceive of, Unicode provides a computer understandable code for that. Now for a complete list of Unicode characters, all of these, this complete list, you can visit this website. Alright, so there are too many to mention here, so if you could just check this link out and you'll find the Unicode for all of the characters. Alright, finally let's talk about error detection codes. Now you know that when binary information, when any information is transmitted, whenever transmission of information is involved, there is always some sort of the possibility of an error creeping up somewhere. Alright, in the entire system, it's not flawless, it's not waterproof, so there is always a chance that when you're transmitting information, there could be error of some sort. So there could be corruption due to noise, or there could be data loss, whatever. The point is, when binary information is transferred, and binary information is what? It's just zeros and ones. So the error that could occur in a binary information is mostly changing of 1 to 0 and 0 to 1. And it's easy to happen, it's easy to occur, but it could change the entire meaning of the whole thing, because that is all binary information is, zeros and ones. So if you change 1 to 0, if during transmission somehow a 1 changes from 0 or 0 changes to 1, that could have significant consequences. So error detection codes are binary codes that help detect such errors during transmission. All right. Parity bit. Now, parity bit is the most common kind of error correcting code. A parity bit is nothing but an extra bit included with a binary message to make the total number of ones in the message either even or odd. So if you're sending, suppose you're sending 4-bit binary numbers across a transmission line. By adding a parity bit, now you'll be sending 5 bits. The additional bit is called the parity bit, and the way it works is, it makes the number of ones in your message, the ones, not the zeros, either even or odd. So this is how it works. Suppose we have a message, 3-bit long message. Suppose the message is 000. Now if we're talking about odd parity, then what you do is add a 1 to it. If the message is 0001, it has odd number of ones, right? So with odd parity, we add a 1. With even parity, we add a 0. If the message was 001, it already has a single 1 in it, odd number of ones in it. With odd parity, we add the number 0, because then the number of ones in the message remain odd. By even parity, I add a 1 to it, and what happens is, now there are 2 ones in the message, so the number of ones become even. Again, if the message was 010, so there is already an odd number of ones in this message. With odd parity, you have to add 0, because you can't change the number of ones to even, but with even parity you can, right? For example, 1110, so it has an even number of ones in it. So with odd parity, if I add another bit 1 to it, the number of ones in this message would then be 3, which is odd. With odd parity, by adding 1, you're making the number of ones in this message odd. With even parity, you add a 0, and then the number of ones remain even. Again, simply, if we had if the message was 111, it already has odd number of ones in it. It has 3 ones. So with odd parity, we would have to add 0. With even parity, we had 1, because if we add 1, then the number of ones in the message become even. So this is how odd and even parity work. So how parity generation and checking works is like this. So at the sending end, the message to be sent is applied to a parity generator, where the required parity bit is generated. This is basically parity generation, right? The message plus the parity bit is then transmitted to the destination. At the receiving end, all incoming bits are applied to a parity checker. This checker checks the proper parity adopted, either even or odd. An error is detected if the checked parity does not match the adopted parity. So on the sending side, suppose the parity adopted is odd parity, right? Odd parity. The point is to make the number of ones in the message odd. The fact that on the sending end odd parity is adopted is transmitted to the destination. So now the destination also knows that the sender has adopted odd parity, which means that it will be expecting the message to have an odd number of ones. That is what odd parity means. So the sender has adopted odd parity, and it has told the destination that it has adopted odd parity. So now the receiver is expecting the number of bits in the incoming message to be odd, and then the message is sent including the parity bit. At the receiving end, the parity checker checks the parity, and it counts the number of ones in the received message. Now, if the number of ones are odd, that means the number of ones are odd and odd parity was adopted, so it means everything was fine. But if due to any error, one of the ones got converted into 0, so now the message has even number of ones, but the parity is saying that it's supposed to have odd number of ones. So there's a confusion. So that is how the checker knows that some error has occurred during transmission. Now this works fine as long as odd number of bits are changed, and you can kind of see why, right? So if suppose 2 bits are changed, if 2 bits are changed instead of 1, so a message that was supposed to have odd number of ones, one of the bit changed, now it has even number of ones. Another bit changed, again it has odd number of ones. So the message is different, 2 bits were changed, but the parity is still odd. So the receiver will think that the message is fine, there's nothing wrong with the message, where in reality 2 of the bits were changed. So this system is very rudimentary. It only works as long as an odd number of bits change. Alright, so that's it for this video. Just a quick recap. We talked about codes, starting from a brief introduction of codes. We discussed binary coded decimal. We discussed gray code. We saw how binary can be converted to gray and gray can be converted to binary. We talked about 2421 code, XS3 code, ASCII and Unicode, and the discussion was concluded with a brief analysis of error detection codes.